Go ahead and open, well, I'm going to want one too, because we need references. So guys, open up your AP equation sheets to the thermochem part, which is the page 4 side. Oh, they changed the order. That's okay. So guys, you've got that open to the page 4 side. You've got your books open to page 184. You've got your class notes that you started previously. And guys, what we're going to do now is complete the conversation that we started last time. So you guys all ready to go? Okay. So if you don't remember, guys, this is the structure, if you will, that we shared when we started talking about heats of reactions, enthalpy changes of reactions. And so guys, what we said generically was 2 times ago, we found out that there are these things called thermochemical equations. And functionally all it is a balanced equation, but then there's this magic delta H value at the end. And these tend to be in kilojoules, but we don't write them kilojoules per mole. They're understood to be kilojoules of moles as represented. So if we've got a value here, that value would be for the amount of X, the amount of Y, the amount of W, and the amount of Z that is either consumed or created in the reaction. Is that all ringing true with you? Okay. Now guys, what does it mean if this value is negative? The reaction is exothermic, and if the value then of course is positive, it's endothermic and energy is going in. Now guys, one other important thought, let's just make sure you're clear on this, because we are going to quantify this in just a second. Guys, where does this energy come from? The bonds breaking and or forming. And so guys, we said this important thing. When reactions happen, what happens to the reactants? They break apart, and is that endo or exothermic? Endothermic, because energy, and guys, picture a rock. If you've got a rock, you've got to add energy to get it to break, right? Bonds are the same. Then guys, our reactants then are forming bonds, and that is always exo, energy off. And then guys, the idea is if this is bigger, then this will be negative. Weird, right? Think about that. If this is bigger, this will be negative because it's exothermic. If this is bigger, this will be positive because you have to take in more energy to break apart the reactants than is given off when the products form. Okay, so guys, big deep breath. Because we've talked about all this conceptually, we're about to talk about the math of what we just said. Any questions about the concepts? You're good? Okay. All right. So guys, with that said, then here's where we are. So this is what we did last time. We talked about all of the empirical ways of coming up with these delta H values. That's calorimetry. We talked anyway. So guys, what we're going to do now is this. We're going to dig down the mathematical side of this. Because guys, it turns out that you can figure out delta H values without ever having to go to lab. So let's talk generically about how. Guys, how could we do this? What information would we need to know in order to figure out delta H values given our previous conversation, what we just talked about? What information do we need to know to come up with these values? Go ahead, Jeanette. So how much energy is in the bonds? Because that would tell us what? Well, the amount of energy that has to go in to break these and the amount of energy that would come out when these form, and then we subtract the two, and that will give us the overall energy change. Does that make sense? Because that's where this is headed. Guys, all of that is what is called Hess's Law. Now, what you're going to see on the AP test is sometimes they will have you, and we're going to do this one first, they will have you figure out these values through computation. And I'll explain that to you in a minute. Sometimes they will have you do this through what we call manipulation. And we're going to finish with that, and that's going to be our day. You guys ready to go? Okay, so guys, first let's define Hess's law. So it goes like this. Guys, Hess's law says this. If a reaction can be broken down into a series of steps, the sum of the enthalpy changes associated with the steps will equal the enthalpy change for the complete reaction, the complete change. I'm going to change change to reaction. Now guys, as you're writing this down, you've got to be careful with the term step. Because when we step, we've got to take step 1 before we can take step 2. Understand that in reactions, this all happens at the same time. So they're separate processes, but they don't necessarily happen sequentially. I have never found myself saying, gosh, I'm really glad I answered my classroom phone. Let's find out. Hello. Hi. Oh, can we all go? Are they going to lunch? Luke, it sounds like you're getting checked out. Can we come? Ooh, very good. He's on his way. Okay, bye. Looks like you're leaving. Did you know? Okay. No, she said no. No, I was hoping, but no. All right. I don't know. I'm not sure, but when it rings, I typically don't answer. All right. So guys, allow me to offer you sort of a weird and yet real world example in some round numbers. So say guys, well, actually, let's do this. So say that I'm going to go on a trip, a road trip, okay? And my plan is that I need to get up to REI up in Salt Lake because I've got to gather together some camping gear. But along the way, I've actually got to run up to Brigham City because a buddy of mine's got some of the stuff that I need. And so guys, I'm going to start here in Orem, or Linden where I live, but let's say Orem. And guys, let's say that I need to run to REI, but I've got to go to my friend's first because he's going to leave and he's not going to be there that long. So I got to run up to Brigham City and then I'm going to come back to REI. So really the trip that I want to take is just from here to REI, but I'm going to go out of my way and I got to go to Brigham City first. So guys, I'm going to leave my house and I'm going to drive 70 miles up to Brigham City to hook up with my buddy. And then from there, I'm going to come back and it's 30 miles back to REI. Guys, the question is this. How far is it from my house to REI? 40 miles. Does that make sense? So guys, looking at it north to south as we travel up I-15, the idea is this. If this is Linden, I traveled 70 miles up to my buddy's house in Brigham City, and then I traveled 30 miles back down, and I ended up at REI. But from that information, we can figure out how far it is to REI because we went 70 miles in one direction and 30 in the opposite direction, and we can see that by bringing these together, the difference is the distance to REI. You get the idea? Guys, that's Hess's law. Except for we're going to do this. We're going to draw diagrams that look like this, where this is energy, and there are no units on the x-axis. And what we're going to do is this. We're going to say these are our reactants. Ready? So if these are our reactants, guys, these things are going to turn into products. But how does that happen? What has to happen to the reactants before they can turn into products? They've got to break apart. So we've got to add energy to break them apart. So this is going to be what we call, and we're going to talk about this more in a couple weeks, these are what are called intermediates. Where the reactants break apart, we have things that are called intermediates. So guys, why do the intermediates have more energy than the reactants? because they had to break apart. To do this, we've got to add energy to the reactants, and we break the bonds inside the reactants, and that's always endothermic. Then, guys, the reactants, the broken apart reactants that we call intermediates, will then form new bonds and turn into products. Now, guys, when that happens, will energy go in or out? Energy comes out, and the energy goes down. Now, guys, if the energy goes out and we end up down here, what's the overall process? Endo or exothermic? Exothermic, because the products have less energy than the reactants. So more energy was given off to form new bonds than was taken in when we broke down the original bonds. Now, guys, what if it does the other? What if we end up with a situation that goes like this, and when these things form bonds, when they rebond, what if it goes like this and the products are up here? Now is it endo or exothermic? It's endothermic because more energy is taken in to break the bonds than are formed when the new bonds form, and that would be an endothermic process. And guys, this is what Hess's law is all about. If we can figure out the amount of energy that goes in to break bonds, and if we can figure out the amount of energy that's given off to form bonds, the difference between those two will be the energy of the reaction. You get the idea? Okay, so then the question becomes, where do we find these energies? And guys, the answer is in what are called enthalpies of formation. So let me define this for you. Guys, an enthalpy energy for the reaction that forms 1 mole of a compound from its component elements. And guys, I know that that's confusing. Write it down and it'll make more sense when we talk about it. So it's the energy change for a reaction that forms 1 mole of a compound from its component elements. Now, guys, it's abbreviated delta H naught sub F. We'll talk more about that after you write it down. So, guys, let's make sure you're clear. You understand what delta means, right? Change. This is heat or enthalpy of formation. But this, do you guys know about that critter? It's actually read as we read it as knot, K-N-O-T. So this is, but what it means is standard conditions, which is 1 atmosphere of pressure, and typically it's 25 degrees Celsius. You don't need to worry about that other than to understand that these values change with temperature and pressure, but just understand that that's what that means. So, guys, the knot means standard conditions, 25 Celsius, 1 atmosphere of pressure. Guys, what I want you to do is I want you to look at the table at the top of page 184. What you have there is a rather incomplete table of enthalpies of formation. Understand, you can look these up for every compound that exists on Earth. It's this. But guys, let's take a look at this table. So let me give you a second to just sort of soak it in. So guys, what are you noticing? What are you learning? What are you finding interesting? Go ahead, Mark. Yes. All right. So guys, let's talk. So you'll notice, and this repeats itself, right? It could be on top of each other and twice the length. So you've got the name of the substance, the formula of the substance, and then its heat or enthalpy of formation. Now, guys, notice that some of these values are negative and some are positive. Now, what does it mean that they're negative? Exothermic. What does it mean if it's positive? Well, it's endothermic, right? And guys, what you'll notice is that most of these are exothermic. What does that mean? When bonds are formed, energy is given off. But now you're looking at this, and for example, guys, if you look at acetylene, that should be troubling to you. Because when these bonds form, energy is taken in. Do you understand why that's troubling? You said, wait, I thought we said when bonds form, energy is always given off. And guys, we are not violating that. So let's talk. So it is true that when bonds form, energy is always given off. Here's the tricky bit. Ready? You all just turned in your chapter 19 outlines, right? Okay, so this is the deal. True or false? When bonds form, energy is always given off. True. But now we look at the heat of formation of acetylene and we go, wait a minute, bonds are forming, but energy is going in. We violated that. No, we didn't. Here's the trick. When acetylene forms, energy is given off, just not in the form of heat. How else can energy be given off? Entropy. That's chapter 19. We'll get there. I know, yuck, right? So guys, this is all you got to understand right now. This is why I didn't have you summarize 19 until now. Guys, understand, we are not violating the rules, okay? The problem is this. Our understanding of energy is too narrow. Energy is always given off when bonds form. It's just not always given off in the form of heat. It can also be given off in the form of disorder, and we're going to talk more about that in chapter 19. Okay, so with that said, guys, let's go back into this table, and let's not worry about the ones that are endothermic right now. So guys, for example, look at ammonia. We're going to use that as our example to figure out what this means. So this says, and I'll just do this on a clean screen, this says ammonia has a heat of formation of -46, and I'm going to drop the decimal, -46 kilojoules per mole. So guys, what on earth does that mean? What does it mean that if it's got a heat of formation of 46 kilojoules per mole? Go ahead, Sammy. Formed.
Yeah, so like whenever you form it,
yep.
It's going to release
yes.
46 kilojoules.
Good. Formed from what? Component elements. And guys, those component elements are H2 and N2. So when this forms from hydrogen and nitrogen, we end up with NH3 forming. Now guys, we don't have to worry about balancing the equations. We don't have to do that, but what we know is this. When we have enough H2 and enough N2 to form NH3, when we form a mole of that, this much energy is given off. So basically what we're saying is the delta H for this reaction is -46 kilojoules per mole. So they give us the products. We assume that the reactants are just the elements that make it up, and that's the amount of energy that's given off in this case when it forms. Yeah?
So I thought we did delta H, it wasn't in kilojoules per mole.
It is now. And the reason is because this will always be 1 mole. Right? So like, for example, the thing that we looked at before, which was CH4 plus O2 yields CHCO2 and H2O. And when we balance one carbon, so we need a 2, and then that's 4. So that was the one that we looked at previously. And whatever this number was over here, whatever the delta H for this was, that was for 1 mole of this, 2 moles of that, 1 mole of this, 2 moles of that. So it's moles as written. But when we look at these heats of formation, it's always relative to 1 mole of product. So we can then say 1 mole, because it's always written so that the product is 1 mole. Is that okay? So guys, go ahead, Jeanette. No, it is from H2 and N2. So it's assuming that these are breaking apart and forming products. Is that okay? But again, the idea is all that they do is they give us the product and the amount of energy that's released when a mole of it forms, and then we just assume that we know that it's the elements turning into the compound. Is that okay? Go ahead. We're going to get into that, and you may have done too much of the homework because we haven't talked about it yet. Yeah, and that's exactly where this is headed. I'll show you in a second. So guys, are we okay? There's one other thing that you need to know, and now we're going to start, and then we're going to start playing with this. You're going to like this. So guys, the only other thing you need to know is this. All of the diatomics are assumed to have enthalpies of formation of 0. H2, O2, N2, Cl2, Br2, I2, all of those. So guys, all of the diatomics are understood to have enthalpies of formation of 0. They're not in the table because they're understood to be 0. So guys, when you're caught up with me here, we're going to go to a clean screen and we're going to play with this. And I got to be honest with you, what I'm about to teach to you, I did not understand in college. I figured what I'm about to show you, figured this out by chance in front of a group of AP students about 6 or 7 years ago. And it was sort of cool. It was like, no way, that's really neat. So guys, what I want to do is show you how this works in the real world, if you will. Can we play together? Okay, here we go. This is I find this interesting. So guys, it goes like this. Do this with me. So CH4 plus O2 yields CO2 and H2O. And then let's balance it. 2 and then 2. Is that right? Okay. Now guys, in days past, we shared the delta H for this reaction. And purposefully, I'm not going to write it down, partially because I don't want to know what it is, but I'm not going to go back and look. We're going to figure out what it is. But guys, in order to do this, we are now going to leverage the table that we have in our book, and we're going to leverage Hess's Law. So guys, let's talk about steps. Ready? And we're going to be writing some stuff down. So guys, in order for this to happen, what has to happen to our reactants? They have to break apart. What has to happen to our products? They have to form. Now guys, what will our reactants break into? Atoms, carbon, hydrogen, and oxygen, right? So guys, let's write that down. So maybe skip a little bit of space and let's write that down. When CH4 breaks apart, what's it going to break into? Well, it's going to break into carbon and it's going to break into 2 hydrogen molecules. Some of you right now are going, oh, I see where this is headed. Now guys, let's do this. When O2 breaks apart, you know what, let's do that differently. Let's break it all the way down to atoms. It doesn't really matter, but I think it'll be easier to see. Let's break this all the way down to atoms. Now guys, when 2 O2s break apart, what's that? What atoms are those going to break into? 4 oxygens. So guys, that is what happens to the reactants. Now perhaps we draw ourselves a line and we understand that this is what happens to our reactants. Now let's look at what happens to our products. And now, Jeanette, I'm going to go back a little bit on what I just said to you, but I think we'll be okay. So now, guys, what happens to our products? Well, now we're going to form products. And Elisha, this is about to get to your question. So guys, one of the products that we're going to form is CO2. But what are the atoms that make up CO2? Well, carbon and 2 oxygens. And guys, what is our other product that forms? Well, it's going to be 2 waters. But what does it take to make 2 waters? It takes 4 hydrogens and 2 oxygens. Did any of you see it yet? From reading? Guys, look at what we just did. We took this reaction in blue and we broke it up into steps. That's Hess's law. But guys, look at the steps that we came up with. What kind of reactions are these two? Synthesis reactions, formation reactions. Guys, what kind of reactions are these? Decomposition reactions. So here we have compounds being formed. Here we have compounds breaking apart. Gosh, if we only had a place that we could look and figure out how much energy is needed to form compounds. Oh my gosh, let's go look in our book. So guys, check this out. Let's start with products first. So guys, our first product is carbon dioxide. Carbon dioxide has a heat of formation, let's write this down, of negative 393.55. And guys, I'm going to move this because I'm out of space. 393.5. Actually, you know what? I still want it there, though, so I'm going to put it here. Reactants, products. That's 395, let's put units, kilojoules per mole. Now, what about water? Well, this is interesting. You see water over there on the right? Yeah, so are we going to use the liquid or the gas? Well, let's put this in context. So, this entire reaction, right, the burning of methane, this is the Bunsen burner reaction. So when that happens, does our Bunsen burner drip? No, so where does the water go? It forms as a vapor. So it would be more appropriate to use water vapor, and that would be negative 285.8. No? Oh, all right. Oh, thank you. Negative 241 point, also 8? Oh, okay. Kilojoules per mole. We good? Okay. Now, guys, let's talk about the reactants. When a reaction happens, do reactants form? No, they break apart. But if these are heats of formation, can't we just flip the reaction over and now all our formations become decompositions? But if we do that, what do we have to do to the sign? Change the sign. So, guys, let's find methane. So CH4, negative 74.8. Is that right? Negative 74.8 kilojoules per mole. Guys, don't change the sign yet. Now, guys, we got to find O2. Oh, it's not there. Oh, it's 0. Okay. Kilojoules per mole. So now, guys, see how this is tying into Hess's law? Because we now have, forgive the loose connection, we now have all the distances. We now know how far it is to Brigham City and how far it is back to REI. What we got to do now is we got to think about the way this is actually playing out. So guys, now we need to doctor this up. So, looking at our reactants. Are reactants forming or are reactants breaking apart? Reactants are breaking apart. So if reactants are breaking apart, what we functionally need to do is we need to turn these into forming processes. And when we do, what else do we have to change? Change the signs, so we're going to make both of these positive. But now, guys, we've got another problem. We have to respect the units. So, guys, how many moles of CH4 did we gobble up? 1. So that's good, because this is kilojoules per mole. How many moles of oxygen did we gobble up? Doesn't matter, it's 0. But, guys, how many moles of carbon dioxide did we make? 1. And how many moles of water did we make? 2. But this only represents 1. So what do we have to do? Do you see that, Elijah? We double it. And now, guys, guess what? If we now add all of these numbers up, that will give us the energy of the overall reaction. So if we go 74.8 plus 0, which doesn't matter, plus a negative 393.5, which is functionally just subtracting it, and then minus 241.8 twice, do you guys get 802.3? Yep, and guys, that gives us the overall energy change for the reaction as written. Just a second. Do you get the idea? Go ahead. Yep. Mm-hmm. Can I get to that in a second? Because the answer is no, and I'll show you why. We're going to do something weird. Guys, thinking just about this reaction, questions? Oh, yeah. Yeah, it's in the back of your book. It's Appendix C. You're going to hate it. Go ahead.
So are all the negatives?
All of the negatives are exothermic.
Or, yeah.
Yes, that's true. Yep. Go ahead.
So what is this negative 802 do? Because we already, it already made the water vapor, it already has everything in it, so what does it represent?
So this number represents the amount of energy that your Bunsen burner will give off when you burn 1 mole of methane. That's the energy that we use to heat water. Is that okay? So guys, do this with me. Quick recap. Don't miss this because this is critical. So guys, it goes like this. What did we just do? Well, what we did is we figured out the enthalpy change for a reaction by leveraging these numbers. What are those numbers? Heats of formation. But guys, look at what we had to do. In order to make this work, why did we have to change these signs? Because they're reactants and they're not forming, they're decomposing. So guys, when we do this, we've got to take the signs of the reactants and change them because they're not forming, they're decomposing. What else did we have to do? We had to multiply by the number of moles in the balanced equation. So guys, 2 things. Multiply by moles, change the signs of the reactants. Get it? Now guys, grab your AP equation sheet. Write this down with me. On your AP equation sheet, page 4, look at the third reaction down. The third equation. Delta H naught is equal to sigma delta H naught sub F minus sigma, this is important, products minus sigma delta H naught sub F reactants. Guys, this equation is this. except for one little oversight. Guys, do this with me. Plug an N in there and plug an N in there. And now, guys, if you want to do this with me, look on page 186 in your book. Look at equation 5.31. See it there? Equation 5.31 is the same equation that we just got off the AP equation sheet. What's the difference? The N. Guys, the AP equation sheet does not include the N, but you've got to remember that it's there. So guys, what does the N stand for? Number of moles. So guys, watch close, listen carefully, and then let's make the connection. So this says this. The heat, the enthalpy change for a reaction is equal to the sum of the heats of formation for the products times the number of moles of product minus the sum of the heats of formation of the reactants times the number of moles of reactants. Now guys, why is this subtraction rather than addition? And the answer is this. Reactants are not formed. Reactants are broken apart, and therefore we have to change the sign. But guys, when you multiply a number, when you subtract a number, what are you essentially doing? Changing the sign. So guys, this equation is this process that made a ton of sense to you in your brains. So all you have to do is find the heats of formation for the products times the number of moles, then find the heats of formations for the reactants times the number of moles, add them up, and then subtract. And the reason that we subtract is because the reactants are being decomposed and not formed. Do you get the idea? Guys, when I figured that out in front of a bunch of students about 7 years ago, I just stood there and went, you got to be kidding me. Because when I learned this in college and in high school, I was just told memorize the equation and plug in the numbers. And then when I had this moment where I was like, this isn't just plug in the numbers, this makes sense. I was like, oh, I just learned something. And it's fun to share. So guys, do you see the connections? Any questions about this? Go ahead. Yep. Oh, it just means a different number of moles. I think it's just trying to indicate to you that the N and the number of moles won't necessarily be the same. Is that okay? So, Elisha, let's get to your question. So, you're going to have to help me think through this. Because, guys, there's a couple ways we can... Elisha's concerned about how we balance these equations. And, guys, we could just do it like this. We could say that ammonia is formed by one atom of nitrogen forming with 3 atoms of hydrogen. And technically that's the case. But we also understand that nitrogen and hydrogen are actually diatomic. And this is actually the way that it works. So guys, this is actually how to balance this equation. With a 1/2 and a 3/2. And when you balance it like that, then we are with 1 mole of NH3, and now the logic works. So whether we want to think of it like this or think of it like that, we always need these to balance relative to 1 mole of our product, and you can actually balance equations with fractional coefficients.
Yeah, so I understood that one.
Okay.
It's just how possible you can have only one half.
Well, because remember, it has to break up in order for it to form products. So the nitrogens have to let go of each other before they can grab a hold of hydrogens and make NH3. So these have got to split. Whether we think of them as already split or gonna split, they have to split. The thing that makes this interesting is what is the heat of formation of all the diatomics? So it doesn't matter in either case. Because however you think of this, the heats of formation of your reactants are going to be 0. Yeah.
I thought that they had to be together.
But again, you can treat it either way, but in either case, mathematically, the value is 0.
So, and can this like exist normally without
Well, and no. So nitrogen left on its own will not stay as individual atoms. It will form molecules. So then we can either acknowledge that and treat this as if we're saying, yeah, we get that nitrogens are together, but we also know the nitrogens have to break apart. So we can also choose to start and say, yeah, the nitrogens already broke apart, let's just start there. Or let's say, no, the nitrogens are together, acknowledging that they have to break apart before they can form ammonia. But in either case, it doesn't matter because the energy that it takes to break them apart is 0. Is that okay? Go ahead.
So when you say we're just gonna like break it apart,
Mhm.
how would you do that?
Activation energy. Remember when we talked about activation energy? We said that there's a hump as reactants become products. We did the stupid putt-putt analogy, and we said that energy has to get the ball over the hump, and if it makes it, it goes to products. That's what activation energy is the amount of energy. It's not quite that simple, but part of what activation energy is the amount of energy it takes to break the reactants apart.
So you like put them in a bottle and heat it up until it got to there.
Mhm. Yeah, yeah, exactly. Yeah, go ahead.
So if those are both diatomics and those are 0, how can it make something that isn't also 0? Like NH3 is -46.
Right. And so the idea is if we were to draw this, if we looked at the energy diagram, we would have our nitrogen and we'd have our 3 hydrogens. And when these turn into products, they actually lose energy. And when they form NH3, the formation of those bonds is actually a net release of energy. There's no input needed because these are already in their elemental form, or as you're getting us thinking, even if they weren't in their elemental form, no energy has to go in to break them apart. They just release energy when they bond together. Is that okay? Guys, great questions. Are we good? Okay, so this is what is called calculating delta H by computation. You're using heats of formation and you're figuring it out that way. Now guys, interestingly, the AP folks actually can also throw you a curveball. Write this down with me. This is called Hess's Law by manipulation. So guys, it goes like this. Say that on the test, you had this question. It says, calculate the enthalpy of combustion of carbon to carbon monoxide. So the first thing we need to do is we need to write a balanced equation for this. So guys, write a balanced equation for the combustion of carbon to carbon monoxide. Go ahead and do it, and then we'll talk about it. So guys, it goes like this. So we're going to go carbon, and we know we want to produce carbon monoxide. But guys, to do that, what do we need to add? Oxygen. But in order to keep this balanced properly, we need 1/2 of a mole of oxygen. So, how do we figure this out? Well, guys, one of the things that we could do is find the heat of formation of carbon, find the heat of formation of oxygen, find the heat of formation of carbon monoxide, and products minus reactants. But guys, sometimes that is not the information that they will give us. For example, and this question was on an AP test, this is the information they gave. Write it down. So carbon, you know what, I'm going to just write this down on a clean screen. It's going to make this easier to work. So guys, here's what we've got. We've got our subject reaction, which is carbon plus 1/2 O2 yields carbon monoxide. And then they gave us this. Carbon plus O2 yields CO2, And that has an enthalpy change of negative 393.5 kilojoules. And then carbon monoxide plus 1/2 O2 yields carbon dioxide, and that has a delta H of negative 283.0 kilojoules. So let me make sure I haven't screwed this up. So carbon plus oxygen, CO2, carbon monoxide plus 1/2 O2 is CO2. Good. Okay. So guys, the question is, how are you going to solve this? And the answer is through manipulation. And so guys, what you're going to do is this. This is our subject reaction. This is what we're trying to figure out the delta H for. To do that, they give us other reactions. And what we've got to do is we have got to manipulate these reactions so that they add up to the subject reaction. So guys, here's the way to do this. Start with the reaction you're trying to study. Start on the left, work to the right. So here's what you're looking for. Type and number of particles. So the first thing we run into is carbon. How many are there? 1. Well, oh my gosh, right here we have 1 carbon. So the number is right and it's on the correct side. So we're okay because we have number and location correct. Then guys, don't worry about oxygens. They work themselves out. But now we come over here and the next thing we run into is carbon monoxide. So guys, find CO in the bottom in our given reactions. Do you see it? Where's it at? The bottom of the second guy. So guys, we've got the right number. We've got 1 CO, but what's the problem? It's on the wrong side, so we've got to flip it over. So we're going to take this reaction and we're going to rewrite it. So we're going to go, I'm going to just erase it and rewrite it. But guys, what we're going to, but you can just rewrite it down below. But I think it'll be easier for you to see this if I erase it and rewrite it. So guys, in rewriting this then, flipping it over, we now have CO2 breaks into, what are our products now? CO and 1/2 O2. Thank you. So guys, we now flip this thing over. Can we just do that? But what else do we have to do? We've got to change the sign of this. Now guys, here's the thing. When they give you these on the AP test, they're not going to throw you all this random crap that you don't even need. What you're going to see is the reactions that they give you to study the subject reactions are the right reactions. So now that we've got number inside correct, now what we have to do is add them up. So here's what we're going to do. We're going to bring down all the reactants. So we've got a carbon, we've got an oxygen, and we've got a CO2. Now over here on the product side, we've got a CO2, we've got a carbon monoxide, and we've got half of an oxygen. Now guys, what we're going to do is we're going to simplify. So we've got carbon on the left, no carbon on the right. We've got oxygen on the left, and we've got half an oxygen on the right. So we're going to subtract. We're going to subtract half an oxygen from each side. There it's gone. Here we're left with half an oxygen. Now guys, we've got CO2 on both sides, so that drops off. And look at what we've got. Carbon plus half an O2 yields CO. Well guys, that is this. And the idea then is this. If these add up to this, then these add up to this. That's Hess's law. So now guys, all we have to do is the math. So negative 393.5 plus 283, because we had to change the sign, and the heat of the enthalpy change for this reaction is negative 110.5 kilojoules. Do you get the idea? So guys, now you've seen it by computation. That's the equation on the AP sheet. Now you've seen it by manipulation, and it'll be clear in the homework and on the test which way to solve it. If they give you a heat of formation table, it's computation. If they give you reactions that you have to manipulate, it'll be manipulation. You'll see. Go ahead.
Do we have to, like, that every time, like, we, like, I get, like, we have to put this, like, change sign, but then we have to, like, choke down and then, like, cancel out?
Absolutely. So if this were on the AP test, they would expect to see that you take these sample reactions and you manipulate them. What about this? What if, for example, this had been, and it doesn't balance that way, but guys, what if this were a 2? What would you do? You would double this and double that. So they expect you to do those manipulations, show the addition, show the canceling, show that they match, because it's this whole logic that supports this math. Is that okay? Go ahead. Down here, so I can't undo without erasing, so let's go through it. So all that we're doing is once we got to here, we just brought down the carbon, the O2, and the CO2, and then we brought down the CO2, the CO, and then we just started canceling things on both sides. So we had a carbon here, but not over there, so it stayed. We had an O2 here and half an O2 over there. So we subtracted half an O2 from both sides. So here it's gone, and here we're left with half an O2. And then the CO2 was here, and the CO2 was there. So we subtracted that from both sides, and we're left with carbon, half an O2, and CO, which is our given reaction.
For some reason, I thought you just canceled out what half O2, which also canceled out CO2.
Yeah. Are we okay now? Okay. You guys good? Okay. So guys, here then is your homework. When we get together on Friday, we are going to dig into chapter 19 and start talking about entropy and all of the madness that is disorder.